Hello viewers, welcome to the fourth lecture on the feedback control. In this lecture we will complete the proof of the theorem which we have started in the previous lecture. In lecture 2 of the feedback control we have seen the following result, that is if you consider the equation x dot equal to Ax plus Bu, where A is n cross n matrix and B is n cross 1, it is a column matrix, and U is a feedback control where K is a column, Kn minus 1, K is a row vector which is unknown, and S is a set mu 1, mu 2 etc. mu n be any set of numbers, real or complex number. Then if the system is controllable, it was shown that if 1 is controllable, we have shown that we can find the feedback matrix K such that the eigenvalues of A plus Bk are mu I is equal to 1, 2, 3 up to. So, this was the result which we have already proved, and the procedure how to find the matrix K was also shown earlier. So, in this lecture, in the previous lecture we have started the same theorem for the general case, that is where A is a n cross n matrix and B is a n cross m matrix. So, that we will see. So, we will see that let x dot equal to Ax plus Bu be the system, the given control system, and here A is n cross n. So, same statement, only the difference is the B matrix is n cross m, S is any set mu 1, mu 2, mu n, and the feedback control U is K times x, where here K is according to the size of the A and B, it is n cross m matrix, m cross n matrix. Okay. So, then if the system is, so the theorem statement is, if the system is controllable, then we can find the feedback matrix K such that A plus B into K has eigenvalues mu I. So, there is no change in the statement except the matrix B. So, for proving this we have already proved a lemma in the previous lecture, that is in the last time we have shown that so if the system is controllable, if the system x dot equal to Ax plus Bu is controllable, then we can find a matrix K1, in this case it is of the size m cross n, okay, m cross n matrix such that the system, now we construct a new system, that is x dot equal to a plus b times k1 into x plus b1 into v. Okay. We change the notation for the control, instead of u, here u is a vector of belonging to Rm, and here v is the real number, it is v of t is a real number. So, it is a single input system. So, what we have done is, from the original system what was given, we have converted into a system of this type where the control matrix is a column vector only. Okay. So, this is in the form which we considered in the second lecture, like B is a column vector. So, we have already shown that we can find a matrix K1 such that this system is controllable. Here B1 is the first column of the matrix B. So, if B matrix is B1, B2 etc. Bm. So, if you take, if the first column is non-zero, we can convert the system into this expression. And we have already discussed, if the first column is a 0 vector, then how to take another non-zero vector from the B matrix and then convert the system. So, this was discussed. So, we assume that B1 is a non-zero vector, and so we convert the given system into this system. Now, we can apply the theorem which was already proved for this type of system. So, the system 2 is controllable, already it is done, and we have a matrix K1 also. Now, since the system 2 is controllable, so this implies there exists, or we can find a matrix, let us say K2 bar, a column, a row vector. So, that is like Kn, Kn minus 1 etc. K1, as proved in the first theorem. That is, if B is a column, then we can find a matrix K, so that such that now the matrix control, the state matrix is A plus B K1, and the control matrix which we are having is K2. So, we can show that such that A plus B K1 is the matrix already given, plus B1 into K2 bar. So, it is a n cross n matrix, this is also n cross n mat. B1 is a n cross 1 matrix and K2 bar is a 1 cross n matrix. So, the product will give n cross n. So, this has eigenvalues mu I is equal to 1, 2, 3 up to n. So, by using the previous theorem, this theorem. So, now we are interested in finding a feedback control for u, that is u equal to capital K into x type of thing. So, for finding this capital K, we make use of this result. So, we have A plus B K1 plus B1 into K bar has eigenvalues this. So, let us try to convert it into this form. A plus B K1 is already there, and in the place of B1 we will write B1 is the first column already there, and we take all the other columns of B matrix, and the first row is from this equation. B1 is the column and K2 bar is a row vector. So, let us take K2 bar as the first row, and remaining rows are all 0. We take a matrix like this, it is a M cross N matrix, it is N cross M. So, ultimately the product will give, because all the second, third, all the rows are 0, the product will give the same effect as B1 into K2 bar. So, we can write it as capital B multiplied by some matrix like this. A plus BK1 is as it is, this one can be written as capital B, and this can be written as K2 matrix, capital K2. So, this can be written as A plus B multiplied by K1 plus K2. Okay. So, this K1 plus K2 is the required matrix K, capital K is nothing but the K1 plus K2. So, this implies, so it is in the form A plus BK. So, capital K is K1 plus K2 is the required feedback matrix. Okay. So, so this theorem is proved for the general case where A and B are. Now, I will just illustrate it with an example quickly, that is in the example. So, this we have already taken, this particular example was done in the previous lecture, 1 0 1 and 0 1 minus 1, and B is the matrix 1 2 1 0 1 1. So, we can easily check that B A B A square B, the rank is 3. So, it is a controllable system, and let us take S to be any set, for example, minus 1 minus 2 minus 3. So, now we want to find a matrix K such that the eigenvalues of A plus BK are the same, minus 1 minus 2 minus 3. So, how to find this K, that was explained in the previous slides. So, quickly if you recall that, so we already have seen that the last lecture, that the matrix K, there exists a matrix K1 which is given by this matrix 0 0 0 1 0 0. such that the system x dot equal to A plus b k 1 into x plus b 1, the first column of B matrix into V of t is controllable. So, this was already shown. So, here A plus b k 1 matrix, if you calculate the matrix, we will get 1 0 0 and 2 0 1 1 1 minus 1 by substituting these matrices, and B 1 is the first column of the matrix B, it is 1 2 1, and so this system is controllable. Now, by using the companion form and the theorem of feedback control, we can find the T such that now we can find T which is of the form, the first row is A, the second row is A into A plus b k 1, the third row is A into A plus b k 1 square. It is a 3 by 3 matrix, non-singular matrix, such that T A plus b k 1 into T inverse will be the companion form, and T into B 1 is 0 0 1. In the standard companion form it can be converted. Then we can find the expression, this A can be found out using this matrix. So, now the A vector, the first row of this T matrix is nothing but 0 0 1 into U inverse, where what is U inverse? It is the controllability matrix obtained from this one B, A, B, etc. here, where the matrix U is obtained from the first, that is B 1. In this system the control matrix is B 1 and A plus B 1 into B 1, etc. we will get, and A plus B k 1 multiplied by B 1 will give 1 3 2, and A plus B k 1 square into B 1 will give the element 1 4 2. So, this is of rank 3 and its inverse will exist. So, this will imply that A bar, the vector, the first row of the T matrix is given by this entry minus 1 1 and minus 1. We can multiply and then get this value like this. So, once you obtain the first row of T matrix, second, third row can be obtained from the formula. So, that implies that T matrix is calculated as minus 1 1 minus 1 and 0 minus 1 2 and 0 2 minus 3. After substituting the proper values in T matrix, we get this one. Now, we want to find this feedback control for this expression, that is we want to find the K2 matrix, so that we ultimately find K1 plus K2. So, for finding K2 we adopt the following procedure. So, we are interested in getting, we want to get eigenvalues -1, -2, -3 for the converted system. So, that implies the characteristic equation is lambda plus 1, lambda plus 2, lambda plus 3 equal to 0. So, that will imply that we get this is lambda cube plus 6 lambda square plus 11 lambda plus 6 equal to 0. So, in the notation of the previous lectures, we see that beta 1 is 6, beta 2 is 11 and beta 3 is 6 again. And the companion form will give the companion form of this matrix A plus BK matrix, or you can say that the characteristic equation of A plus BK1 matrix is the characteristic equation of A plus BK1 matrix. So, that is given by directly if you calculate we will get lambda cube minus 2 lambda plus 1 equal to 0. So, from the standard notation we get alpha 1 is 0, lambda square term is not there, alpha 2 is minus 2 and alpha 3 is 1. So, if you recall from the second lecture of this one feedback control, we see that the expression gamma value, gamma I is alpha I minus beta I. So, that will imply that alpha 1 is minus 6, sorry, gamma 1. So, we get gamma 1 is minus 6, gamma 2 is minus 13 and gamma 3 is minus 5. So, from this calculation we will get finally we get, then again recall the method which we have seen in the second lecture, that is gamma multiplied by T inverse. The row vector k is given by gamma multiplied by T inverse, and so once we calculate this, then we can calculate the K2 vector, which we require actually in this procedure. We are defining this K2 vector, where K2 vector is the first row is the matrix which we found and all the other rows are 0. So, after finding this K2 bar, we will put this K2 bar in the first row and then all the remaining rows are 0. Say matrix n cross m, m cross n matrix. Okay. So, then the required matrix is K1 plus K2. So, this can be calculated by because all the values are available, gamma is there, T inverse is there, by substituting we get the feedback matrix. So, if we substitute this, so the feedback control the u of t which belongs to Rm, that is k times x of t. Okay. So, the feedback control is given by u of t equal to k into x of t, and then the matrix A plus B into k has eigenvalues -1, -2, -3. So, this can be easily verified by actually calculating the eigenvalues. So, now if you see here, the main assumption in this theorem is that the system x dot equal to A x plus B u is controllable. But in case the system is not controllable, then is it possible to find a feedback control in this similar form. So, that we will briefly see, because we have some procedure for controllable system, and now we will reduce the non-controllable system into a system which has two parts. One portion is controllable portion, another portion is non-controllable portion, and then we can apply the same theorem for one portion, that is which is controllable portion. Okay, so, consider the system x dot equal to A x plus B u, which is not controllable. So, that means the rank of the matrix, the block, first block is B, second block A B, and A power n minus 1 B. This rank is equal to, let us say, R, which is less than n. So, then can we apply a similar theorem? Can we find a feedback control? That is the question here. Now, let us consider the matrix like this. So, let R be the matrix containing because the rank is R here, we can select R columns from the matrix U. Let us call it as U matrix, where U is B, A, B, etc. The size of the matrix is n cross m into n, but only R columns are linearly independent because rank is R. So, we select any R column which are linearly independent from that and put it as a matrix containing. So, let R be the matrix containing the linearly independent columns of U, or any linearly independent columns we can select, R of them are available. So, let R is equal to, the first column is R1, second column is R2, and R suffix R. So, this notation is not. So, now let us take a matrix P such that it contains the linearly independent columns or linearly independent columns given by, let us say, P1, P2, etc., P suffix R. And so, let us take P R plus 1, P R plus 2, etc., P n or remaining linearly independent vectors which generate the entire space such that the entire set P1, P2, etc., PR, that is already taken from the U matrix, and PR plus 1, PR plus 2, etc., Pn. and so this forms a basis of the space Rn. So, let us write the matrix as, so let us consider the matrix P1 P2, okay, the block of this one. Here the notation we can consider, instead of P we can consider as P1 and P2 is the remaining matrix, okay, where P2 is given by P r plus 1 etc. Pn. So, the column vectors are like this. So, it is a matrix n cross n minus m matrix, and this is a square matrix n cross n matrix, and P1 matrix, capital P1 matrix is n cross R matrix. Okay. I think there is some notation problem, R plus 1 etc. Rn. 1 minute, you can cut it now like little bit, n minus R. Okay. So, we have the matrices P1 of this size and P2, and P1 P2 forms a matrix capital P. Okay. So, now consider the equation x dot equal to Ax plus Bu. If we multiply both sides by this P inverse matrix, we get P inverse Ax P inverse Bu, and if you let y is equal to Px, P inverse x here, we get, from this equation we get y dot equal to P inverse A, y can be, x can be written as Py and plus P inverse Bu. Okay. So, let us write this P inverse as the matrix, another matrix Q1 Q2 as a block matrix. The first block contains R rows and the second block contains, so Q1 is a R rows and n columns, and Q2 contains n minus R rows and n columns. And so, if P inverse and P, that is identity matrix, and if you actually multiply P inverse and P matrix, we will get Q1 into P1 and Q1 P2, Q2 P1 and Q2 P2. These are block matrices. Q1 is of the size, and P1 we have already seen it is n cross R. So, the first one is the square matrix R cross R matrix. So, accordingly we can find the size of this one. So, if identity matrix also should be divided into I, this will be R cross R, and this is the remaining n minus R cross n minus R size, the remaining are 0. So, from this notation what we get is Q1 P1 is identity and Q2 P2 is identity, the remaining are 0 matrices. So, in particular we are interested in this Q2 P1 is the 0 matrix, okay, of the proper size, whatever size we have. Now, if you observe this P1 P1 matrix contains all the vectors which are in the controllable matrix B, A, B, etc. This equation Q2 into P1 equal to 0, it implies that all the columns of P1 and the rows of Q2 they are orthogonal to each other, because the row of Q2 multiplied by a column of P1 gives the 0 element. So, it implies that Q2 is orthogonal to the columns of P1. So, that can be utilized. And if we observe this U matrix, it is generated by the columns P1, P2, PR. So, all this matrix A B, A square B, A power n minus 1 B, all these columns are generated by the elements of P1, P2, PR, because there can be only maximum or linearly independent columns for this. All the columns are generated by P1, P2, PR. So, the matrix B, A B, A square B, all the columns are generated by the matrices, the vectors P1, P2, PR. So, here Q2 P1 equal to 0, it automatically implies the various other things. If we observe this equation y dot equal to P inverse APY, y dot equal to P inverse is written as Q1 Q2 and A is there, P is written as capital P1 capital P2 multiplied by y plus again P inverse, that is Q1 Q2 multiplied by B into U. So, this is the equation in the this notation introduced in this page. Okay. So, this implies that Q1 Q2, the first matrix, multiplied by matrix A multiplied by this block y dot equal to Q1 Q2, and this product will give A P1 is the first block and A P2 is the second block multiplied by the vector y, and this can be written as Q1 B is the first block and Q2 B is the second block multiplied by the vector U. So, again we multiply the Q1 block with the AP1. So, this will give Q1 AP1 and Q1 into AP2, Q2 AP1 and Q2 AP2 multiplied by the vector y, and this is as it is Q1 Q1B and Q2B multiplied by U vector. So, now we can make use of the thing here Q2 P1 equal to 0. It means the rows of the matrix Q2, they are all orthogonal to all the vectors P1, P2 etc. And so, that implies this step itself will imply that Q2 into B equal to 0, because B also is part of the U matrix and all the columns of U matrix are generated by P1, P2, PR. So, if Q2 is orthogonal to all this P1, P2, it should be orthogonal to B as well as A B, A square B etc. So, this implies that Q2 into B is 0, Q2 into A B will be the 0 matrix etc. So, we can easily get this expression Q1 A P1 and Q1 A P2, but here Q2 is orthogonal to all the elements, all the columns of U. So, A P1, A P2, all of them are columns of U. So, this will be the 0 block, and here it is Q2 A P2, we get Y, and here it is Q1 B, but Q2 into B is 0, okay, 0 block by the previous one. So, this separates the system into very simple form like this. So, if we write Y to be it is a Rn vector, we will write it as y1 vector and y2 vector. First R elements are called y1 and the remaining n minus r elements are called y2. So, if you write like this, then we get from the previous page we will get y1 dot this the derivative of y1 is Q1 A P1 into y1 plus Q1 A P2 into y2 plus here Q1 B into U vector we will get. Okay. Similarly, y2 dot will be 0 into y1, so that will not come, Q2 A P2 into y2 plus 0. So, we will get the simple form y1 dot is equal to A1, that is Q1 A P1 y1. So, y1 dot is Q1 A P1 into y1, this matrix, plus Q1 A P2 into y2 matrix plus Q1 B into U. Okay. Similarly, y2 dot it will be Q2 A P2 into y2 and plus 0. So, this system we can see that there is no control at all, simply it is a separate system, it is a dynamical system, and only first system is having a control. So, this system is controllable, actually this y1 it belongs to a r dimensional vector space, and we already saw that this system is controllable because the rank of the controllable matrix is R here, it is equal to the control space. So, this system is controllable, it is divided into two systems. The first system is controllable and the second system has no control at all. So, it is not controllable. Now, we can find a feedback control for the, because the first one is controllable. So, since equation 1 is controllable, because we can assume that this y2 is a known quantity, we can easily solve this differential equation 2 and then substitute the value of y2 in the first equation. So, only y1 is the state variable for the first equation and u is the control variable, and y2 is a known value because of the dynamical system. So, this system is controllable due to the rank condition. One is controllable, we can find suitable feedback control. Using the previous theorem for the controllable systems. So, we can make use of this theorem for controllable system and find a appropriate feedback control for any required eigenvalues of this thing. So, I will complete this lecture with this example. Thank you.